Hello, honors chemistry students. In this video, we're going to go through what I think are the most commonly missed questions in the unit review. And then at the end, we're going to go over the most commonly missed questions from the Schoology quiz over the gases unit. And those questions specifically are what Schoology said were the most commonly missed questions. Okay, so I'm not going to go through all of them. If you do have specific questions, just send me a Schoology message, but I'm going to go through what I consider to be the ones that I've seen a lot. So in question 1, just make sure all gas laws for temperature always needs to be in Kelvin. Okay, that is something that there will be a question on your test and it'll give you degrees Celsius, and for some of you, unfortunately, you'll probably plug in degrees Celsius, so just try not to make that mistake. So temp must always be okay. Now, in question 2, you need to make sure that you're able to convert to different pressure units. We'll talk about when different pressure units are best, but if you're ever in doubt, just put your pressure units in atmospheres, and chances are you'll be good. Those pressure conversions, they're on the back of your periodic table in the gases section, and you just need to know that 1 atmosphere is the same thing as 760 torr, which is the same thing as 760 millimeters of mercury, which is the same thing as 101.3 kilopascals, okay? So from there, and this key will be posted online so you can look at my conversions, but this is what I use to do any sort of gas conversions. Okay, so in question 3, this is Dalton's law of partial pressures, and what it states is that the total pressure of a gas mixture is just equal to the pressure of gas 1 plus gas 2 plus however many gases there are. So that could really go on for quite a bit. The only thing that's kind of tricky with this question is it says that we've got oxygen, argon, and nitrogen. So we've got 3 gases, and oxygen has a partial pressure of 99 millimeters of mercury. Nitrogen has 0.33 atmospheres, and the total pressure is 675 millimeters of mercury. So the only thing here that I think is a little tricky is that it looks like getting everything to millimeters of mercury would be most helpful to us. So what I'm going to do is I'm going to take 0.33 ATMs, and I'm going to use my conversion from up here, and atmospheres, millimeters of mercury, using our dimensional analysis fence method. I'm going to take ATMs down here, millimeters of mercury down here, and 1 atmosphere is 760 millimeters of mercury. So I'm going to multiply those two, and I get 250.8 exactly. And so what I'm going to do is plug in my total pressure. That's 675. This is equal to the pressure of oxygen, and that pressure of oxygen is 99. So we'll change this guy to O2. We'll change this guy to nitrogen, N2. And nitrogen was 250.8 millimeters of mercury. And then our third pressure, that's unknown, that's going to be argon. So P of argon, I'm going to subtract 99, and I'm going to subtract 250.8 from each side. Oops. And when I do that, I get 325.2 millimeters of mercury, and that's the pressure of just the argon gas. Okay, number 4 is one that a lot of people know, and but then they don't apply it, it seems. So pressure is caused from gas particles bumping into the walls of their container. Okay, what does not cause pressure is particles bumping into each other. They will bump into each other, but that does not cause any pressure on your container, okay? So if we have something like this is pressure. But if we have something like this, where two gas particles hit each other, that is not going to cause pressure. Okay, so that's something that you just want to make sure you know. Okay, so in question number 5, it says, which flask contains the most moles of gas? It appears that the flasks have the same size, and we can assume that they're all at the same temperature. So if I use the ideal gas law, PV equals N RT, volume appears to be the same. R is always going to be the same. It's just a gas constant. And T, we'll just assume it's the same. So which one has the most moles? Well, we got to look at our pressure. So it's either going to be the container with 1 atmosphere or 4 atmospheres. And it's actually going to be the container with 4 atmospheres. Okay, pressure and moles have a direct relationship. So if we hold the volume constant, which it appears to be here, then the container with the most pressure will contain the most moles of gas. Okay, and if you plugged in numbers into PV equals nRT, that would be proven. Okay, if each container contains the same moles of gas, which container has the greatest pressure? Okay, so we're going to do PV equals nRT. We're going to assume that we're at the same temperature. We're going to assume we're at the same R. And they tell us that we have the same moles of gas. So which one has the greatest pressure? Well, imagine yourself, if you had a balloon, you'd blown up, and you pushed with your hand, you squeezed the balloon from the outside and increased the pressure of the gas molecules inside that balloon. Think about what would happen to that balloon. Would it expand when you do that and you push on it, or would it contract or shrink? And the answer is that it would shrink. So pressure and volume have an indirect relationship. So since each flask here has the same amount of particles, the particles in the flask, specifically flask 1, actually, to create pressure, they don't have to travel very far in comparison to the gas particles in flask 4. So flask 1 is the container that has the highest pressure. Okay, so let's look at number 8. I'm going to show you a couple ways to derive each gas law. And so here we have a balloon. It's got a volume of 5 liters and a pressure of 2.5 atmospheres. What would be the balloon's volume if the pressure changed to 1.5 atmospheres? So what I call this is a before and after gas law problem. And what that means is we will need to derive the equation. There's a couple ways to do this. One is to say, okay, our ideal gas law is PV equals nRT. We've got pressure and volume. We're not dealing with moles, R, or T, so our equation would be PV equals PV, where our left-hand side is our before situation. Those are marked with 1s. And our right-hand side are marked with 2s, and those are our after situations. Okay, that's one way to come up with the formula. Here's a second way. On the back of your periodic table, you'll see what's called the combined gas law, and it looks like this, I believe. You might have to just take a second to find it. Oops. But this is on the back of your periodic table, and another way to come up with each gas law is to say, okay, they give us pressure, they give us volume. We're not mentioning moles or temperature, so our equation is just going to be P1 V1 equals P2 V2. Now, when you use an equation like this, a before and after gas law problem, temperature, which isn't important in number 8, but will be in other questions, has to be in Kelvin. That will never change for any problem. However, here, it doesn't matter what units I use for pressure or volume. All that's important is they have to be the same units. Okay, because we're going to end up dividing them by each other, so the units will cancel so long as they are the same units. So to plug everything in here, We've got P1 V1 equals P2 V2. The initial pressure is 2.5 ATMs. The initial volume is 5 liters. The new pressure is 1.5 ATMs, and the new volume is V2. We're going to divide by 1.5. That causes 1.5 on the right to cancel, and we're left with 2.5 times 5. That'll be 12.5 divided by 1.5. And I get 8.3 repeating, so 8.3 liters equals V2. I knew V2 was in liters because V1 was in liters. So let's say if they gave you milliliters, then V2 would be milliliters. This makes sense to me because if I let a balloon expand, that will allow its pressure to decrease. We saw a decrease in pressure. And if the balloon's expanding, then the volume should increase. Okay. In number 9, go ahead and read this one, and I want you to diagnose it. Is it a before and after gas law problem, or is it not? Okay, when I read this, it is not a before and after gas law problem. The reason I know is just from the wording in my context clues, it does not appear that any of our variables, whether it be temperature, liters, or pressure, none of those seem to be changing. And so when that's the case, that just means it's an ideal gas law problem. So PV equals nRT. And when we use PV equals nRT, you need to use this R value, 0.08206. And in other times when I do this, I round it to 0.0821. So if you use 0.0821, no worries. If you use 0.0826, no worries at all. And we've got ATMs times liters divided by moles times Kelvin. And those units on R are incredibly important because for everything to work out, these are the units that we need. So if we're going to plug in a pressure, it needs to be in atmospheres, okay? That's what our R tells us. So we do have atmospheres here, 1.05 atmospheres. So we'll plug that in. If we're going to plug in volume, it needs to be liters, okay? So we're given liters, so we can plug that in, 3.50 liters. We're asked how many moles, so N is always kind of a weird variable to learn at first, but N stands for number, and I would tie those together, those N's, number of moles. Okay, and then our temperature, a lot of people will plug in 21 degrees Celsius, but that will not be right. We've always got to make sure we get it to Kelvin, so to get Celsius to Kelvin, we just add 273. And we get 294. So the math here is we need to isolate our variable N, 0.08206. That'll get those to cancel. We got to do that on both sides though. And then divide by 294. And so I'm going to plug this exactly how it looks into my calculator. And if you're using one of those scientific calculators, here's what I would plug in. 1.05 times 3.5, and I would just use the parentheses just like so, divided by 0.08206, and then another division sign just to keep this 294 in our denominator. Okay, on the quiz, one of the most common mistakes was just calculator errors, okay? So I just don't want anyone to run into that on the test. Okay, so let me plug that into my calculator. 1.05 times 3.5 divided by 0.08206, and then another division sign, 294. And our moles, which we never expect a lot of moles, okay, because 1 mole is 6.02 times 10 to the 23rd particles, which would be a lot. 0.152 moles of gas. If this question, which some questions later on will ask for grams, we just go from moles to grams, but we have to know the identity of that gas. Okay, now some of you I'm sure are wondering, can I do this question like so, where I do PV equals nRT? We know we need to solve for N, so we're going to divide over RT, and then do PV over RT equals N, and now plug in numbers, absolutely. That is a great way to do that as well. Okay, now I'm going to do just a couple more of these gas law problems just because I want to show common mistakes that people tend to make. And so I'm going to look at number 11. It says a balloon has a volume of 1 liter at 21 degrees Celsius and 750 millimeters of mercury. What is a balloon's volume if we change our conditions to STP? If you remember, STP means we're at 1 atmospheres of pressure, and our temperature is 0 degrees Celsius. So what I'm going to do is say PV equals nRT. I have pressure, volume, and temperature here. If I use my combined gas law and cross out what I don't need, what I'll do is say, okay, N was not given. They didn't mention anything about moles. So my equation simplifies to P1 V1 over T1 equals P2 V2 over T2. Okay, and that would check out here if we divide each side by T. Okay, now let's plug in what we need to plug in here. Okay, so our initial pressure is 750 millimeters of mercury. With a before and after gas law problem, we can plug in any sort of pressure, but if I'm going to choose millimeters of mercury here for P1, then what I'm doing is I'm saying P2 needs to be millimeters of mercury. Okay, so if you wanted to stick with atmospheres here, just, if you always want to do atmospheres, that's fine as well. Our volume is 1.0 liters. Our temperature is 21 degrees Celsius, which I think on the last problem we saw, and this is 294 Kelvin. We are going to a new pressure, 1 atmosphere, so 1 ATM. In 1 ATM, there's 760 millimeters of mercury. So that'll solve to be 760 millimeters of mercury. We are solving for the new volume, that'll be V2. And then 273 Kelvin will be our temperature. And most people really set this up just fine. It's the math that sometimes gets in the way. When we have fractions, those are kind of hard to work with sometimes. So my recommendation is just to cross multiply to get rid of fractions. And so when I do that, I'm going to get 750. I'm going to ignore units right now because when I solve for V2, if V1 was in liters, V2 needs to be in liters. Times 1 times 273, that's this cross multiplication. That equals 760 times V2 times 294. I'm going to divide each side by 760. That'll get rid of that. I'm going to divide each side by 294. And V2, let's see what that ends up being. 750 times 1, which I don't really need to do, times 273, divided by 760, divided by 294. And when I do this, I get 0.916, and I need to make sure I put liters on there. Okay. So I want to talk through a couple of them. Number 13, and you're more than welcome to bounce around here. I'm just going through what I consider to be ones where people might have problems. Number 13 says a 10-gram chunk of solid CO2, which is dry ice, sublimates, meaning it goes from solid to gas. What is the volume of that gas measured at 27 degrees Celsius and 740 millimeters of mercury? Okay, so what I'm going to do quickly is I'm going to say PV equals nRT. I'm looking at my key just to tell you this is 0.974 ATMs. We're solving for volume. Our moles, I'm taking 10 grams of CO2 using the molar mass, and I'm getting it to moles, 0.227 moles. 0.0821 ATMs times liters divided by moles times Kelvin. and our temperature is 300 K. Okay, when I solve for volume, and this, again, this is not my part, this is not why I'm going over this, we get 5.9 liters. It says, what is the density of this gas? Well, if you remember, density equals mass over volume. So what we can do is plug in 10 grams of CO2 and divide it by the volume, which is 5.9 liters. And when we do that, we get 1.85 grams per liter. Okay, now, what you may be wondering, and I'm just plugging it into my calculator to verify, just give me 1 second. Is we've got an equation, molar mass equals dirt over P. Can I plug in the molar mass, plug in P, T, and R, and solve for density that way? And the answer is absolutely. Okay, that's a really good equation to use. And that one's on the back of your formula sheet as well. Okay. So, number 15 is actually that exact question. It just says, what's the density? So I'll do this one really quickly. We're at different conditions, so we're going to get a different density, but chances are it'll be pretty similar. So molar mass equals dirt, dRT over P. The molar mass of carbon dioxide is 44.01 grams per mole. We're solving for density. R is 0.0821. Atmospheres times liters divided by moles times Kelvin. And then our temperature is 310 Kelvin. Okay, and then our pressure is 1.05 atmospheres. And what I'm going to do is I'm going to cross multiply. So I'm going to get 44.01 times 1.05, and that's going to equal D 0.0821 310 divided by 0.0821 divide by 310 as well. And when I solve for density in my calculator, I get 1.82 grams per liter. Okay, now I want to go through and I'm going to jump around here quickly. I'm going to do question 19 quickly, and then to balance this one's actually kind of hard to balance. 4, 5, 4, 6. We are at STP, and one thing that people kind of struggle with a little bit is to understand that 1 mole of gas equals 22.4 liters only at STP. Okay, only at standard temperature and pressure. If you're not at STP, you're going to have to use the ideal gas law, and we're going to see that on our next question. So here we are given 26.8 liters of water vapor, so we're at the star, and we need to convert it to grams of NO. So what I'm going to do is I'm going to take 26.8 liters of H2O. Good rule of thumb in chemistry, if you're ever in doubt, try to get to moles. Well, there's 22.4 liters of H2O and 1 mole of H2O, and that's only at STP. Now that we're at moles, we're at that critical mole step, or mole bridge step, I should say. And there are 6 moles of H2O and 4 moles of NO. We're asked for grams, so what we need to do is say that in 1 mole of NO, there are 30.01 grams of NO. When we solve that out, we're going to get 23.94 grams of NO. Again, when I solve that answer, I'm not sure if it's right, but at least it's not millions and billions. So that makes me feel pretty good. Okay, so then what I'm going to do is I'm going to look at question 17 now, and this one's not at STP. So let's see how things are different if we're not at STP. First of all, this is already balanced. And it says how many grams of calcium carbonate. That is a major part of limestone. Think about limestone is bones from like fish and different animals that have fallen to the bottom of the ocean. And what does the ocean have a lot of? Well, carbon dioxide. That's why there's so much fizz in the ocean, if you've ever been to a beach and the waves crash upon the shore and they fizz. Additionally, the bones from fish and other organisms have lots of calcium in it, so they form a compound known as calcium carbonate. Okay, so we're asked to solve for grams of calcium carbonate, but we're only given information on carbon dioxide. Okay, so what we need to do is just mole bridge to calcium carbonate and then go from moles to grams. However, we're just given volume, temperature, and pressure, so the only way that I know of to get to moles, and this is moles of carbon dioxide, since the pressures for carbon dioxide, the volumes for carbon dioxide, is to use PV equals nRT. That's called the ideal gas law. We'll plug in 1 atmosphere, 4.29 liters. That equals N of CO2, 0.08206 ATMs times liters divided by moles times Kelvin. And then our Kelvin is going to be 300 Kelvin. Okay, so when I do that, and I'm going to trust at this point in the video you've gotten your math straightened out, we get 0.174 moles of CO2. Once I have that, this question shouldn't be so bad. I just take 0.174 moles of CO2 and 1 mole of CO2. There's 1 mole of calcium carbonate. When I look at my periodic table, calcium's 40.08, carbon's 12.01, and then 3 oxygens would be 48. So 1 mole of calcium carbonate is going to be 100.09 grams of calcium carbonate. And when you math this out, we get 17.42 grams of calcium carbonate. Okay, so those questions that I just went over tend to be the ones that I see people have hiccups on. Overall, people generally do pretty well on this test. I'm going to go over the most missed quiz questions right now. So the first one was number 4, and it says, according to kinetic molecular theory, which can be abbreviated KMT, all the following are true for a mixture of gases at the same temperature except. So, gas particles create pressure when they bump into other gas particles. That is not true. Okay, so I think that's going to be my answer, but let me read through all the others. Gas particles create pressure when they bump into the wall of their container. Absolutely. Gas particles are farther apart than liquid. Absolutely, we see liquids as something that looks like this. And then gas, they're definitely farther apart because they have more energy. Gas particles are in continuous motion. Absolutely. And then gas particles at the same temperature have the same kinetic energy. And this has to be true. One thing that if you were in class and we were doing this, this would not be a tricky idea, but temperature is just a measure of kinetic energy. So if you're at the same temperature, by definition, you have to have the same kinetic energy. Okay. Which is the correct statement of the content of the flasks below? Okay. Part 1 says the number of molecules in each flask is the same. That is true. The reason why is if I did moles, 1 mole is 6.02 times 10 to the 23rd particles, or molecules, whatever you want to say. I'm going to get the same answer, okay? I'm going to get that 6.02 times 10 to the 24. Or excuse me, 22, because they all have the same moles. So that has to be true. So automatically, I can get rid of those 3 answers. The pressure inside each flask is the same. Well, the flasks appear to be the same. So let me just think about PV equals nRT to see if I can think through this. The volume tends to be the same. We know the moles are the same. R is the same. And I guess we'll assume that the temperature is the same. So mathematically, the pressure has to be the same. So that's actually true. And then the density of the contents in each flask is the same. Well, density is equal to mass over volume. The volume is the same. Let's just say they're 5 liters. I don't know that that's true. But is this grams the same? Well, an easy way to check that is by going, so for example, neon. 1 mole of neon is 20.18 grams, I believe. Let me look up krypton really quickly. krypton, according to Google here, because I'm not looking at a periodic table, 1 mole of Kr is about 83.8 grams. And so mathematically, we can see that those will not be the same mass. So 3 is not correct. So 1 and 2 are correct. 3 is not correct. So that would leave you with answer choice D. Okay, and then this was the last most commonly missed question on the quiz. We are not at STP, and we are trying to get mass of potassium chlorate. So we're given oxygen. So we start here. We're trying to get over here. We got to do pressure of oxygen times the volume equals moles of oxygen, RT. The pressure is 1 atm. That looks good. The volume is 29.5 liters. We're solving for moles of oxygen, 0.08206 atms times liters divided by moles times Kelvin, and then times 400 Kelvin. Again, I'm going to trust that your math is good here at this point. I'm going to take 29.5 divided by 0.0821 or 0.08206 divided by 400, and I get 0.899 moles of oxygen. 0.899 moles of oxygen is not what I want. I want mass of potassium chlorate. So there are 3 moles of oxygen for every 2 moles of KClO3. This is my mole bridge. And then in 1 mole of KClO3, let me calculate that really quick. 39.1 plus 35.45 plus 48. We get 122.55 grams of KClO3. 0.899 times 2 times 122.55 divided by 3. We are going to end up with 73.4483 grams, which would have been this as our answer.